All right, so this is on red-black trees. So some invariants on RB trees. So every node is either colored red or black. There cannot be two consecutive red nodes. Okay, if there are two consecutive red nodes, then you're going to come across one of those rotation cases. Every path from a root or any other node in a tree to a leaf has the same number of black nodes. And this is precisely what makes this RB tree balanced. And by any other node, I specifically mean non-leaf nodes. LLRB, which is a left-leaning RB tree, has red nodes to the left. That's precisely why it is left-leaning. If you had a right-leaning RB tree, then you would have red nodes on the right. New nodes that you insert are colored red. And this is before you do any restorations to these invariants. For example, before rotating or before color flipping. And the biggest thing to kind of remember about RB trees is, and this is really helpful for drawing out what the result of a rotation would be, is that the RB tree is really just another BST. It's a colored form of a BST, right? We just color every node as either red or black, but really at every level of your RB tree, the BST invariants are satisfied. And again, this is just kind of a naive way of representing the invariants. You can use compare to if they're not primitives, right? If they're objects that you have to compare. Okay, and so let's look at some restorations that we can do to satisfy these invariants at every step. So first, we have some rotations. We have left and right rotations. So I just wanted to do some examples, and these are pretty general. So we have, we're just going to be focusing on 3 nodes mostly. So we have this P, which represents all the nodes that are kind of above this particular subtree that we're looking at. And so, for example, if A is not the root, then it's probably going to be pointed to by some other node up here. And so I'm just denoting all of that subtree as P to kind of abstract away from that. And so we're really only focusing on A and B, and all of this to the left of A is things that are less than A. All of these are things that are between A and B, and these are all greater than B. Okay, and again, I can define these relationships precisely because I know that an RB tree is just a BST. It satisfies those invariants. So if I do a left rotation on A, right, what happens is I basically sever this connection. First of all, I need to actually create 2 pointers to A and B. Then I sever this connection. Then I have A pointing to this one. And so now I can just remove B's pointer to that because it's redundant. And instead, I have B point to A. Right, so if I just kind of redraw everything, right, so then B is now going to be at the top, B is now going to be the new root of this subtree, and then A is going to be its left child. I don't know why I keep erasing things. And then everything is just going to settle based on the invariants, right? So even if you didn't know where all of these would go after the rotation, you can actually determine where they would go just by looking at the relationship to A and B. That's why I say that noticing or realizing that RB trees just satisfy the BST invariant can be really helpful to determining what the result of a rotation would be like. And similarly for right, except it's symmetric. So again, we have this type of tree. I flip the B and A. So really this is exactly the same thing as the end result of left rotation. And remember that all these rotations are basically fixated around a certain node, right? So you have to pass in which node you want to rotate around. And in this case, we're rotating around B, which is different from what we rotated around for left. But basically, it's kind of the same thing symmetrically. So we have A now becoming the new root, and then everything to the left of A is smaller than A, everything to the left of B is in between A and B, and everything to the right of B is greater than B. We also have some operations, specific operations that we do to restore these invariants. So basically rotations here was just kind of getting introduced to what these rotations are actually doing. And now to see what scenarios we could apply them in is really helpful when we actually start inserting nodes into an RB tree, and specifically left-leaning RB tree. So because it's left-leaning, we always want the right child to be on the left. So if we come across a scenario where it's on the right, this is really bad. This is a right-leaning RB tree. This is exactly the opposite of what we want. And so we just rotate left to get everything on the left, right? And notice that first, I do everything colorblind. right? So I just copy the color that they were here into this result of the rotation. So C was red here, so C is red here. A and B are black, so they're also black here. But now, I always have to remember that I have to swap the colors of the nodes that I rotated, right? So if I was rotating based on A, right? And so now A and its its substitute, basically, which is going to be C, have to switch colors. And so C is now going to be black, A is now going to be red. And so this is how we make sure that the red child is on the left. Okay. And also just a good thing to remember is that when you look at something like this, right, CA in this example, we have a black child and then you have a left-right child. That means that the right child is part of the black node, right? So if you transform this red-black tree into a 2-3 or even a 2-4 tree, then it probably means that your red node is going to be in the same key as your parent black node, assuming that your red child is actually the left child. Okay, that was a lot of words. Now let's look at the second scenario. So let's say that we have 2 red children in a row, right? This is also forbidden. And so what we need to do is we need to rotate right. Okay, so now B becomes at the top, and this is actually a more balanced tree, right? Well, the colors kind of seem really weird, and it is weird because we forgot to swap them. So again, we need to swap the colors of A and B. We're rotating based on A in this case. Let me just actually specify, rotate left on A. Right, so we need to swap the colors of A and B, and so B becomes black, A becomes red, and now we come into this third scenario of having 2 red children. Having 2 black children are okay, but having 2 red children are not okay. So in this case, we need to flip the color. So we need to have B become red, we need to have C and A become black. And now in the special case where B is actually the root of our entire LLRB, then because the root always has to be black, we just make it black. Okay, so in this case, all 3 nodes are going to be black. And let me just actually add that as an invariant. So 7, every root node has to be black. So even after color flipping, it becomes red, you have to change it back to black. All right, so let's look at some examples of how all of these scenarios work when we insert stuff into an RB tree. So again, we're assuming LLRB. And right now we have inserted M, D, and B. And so basically, based on lexicographical order, it's going to be all left-leaning, right? Which means that we've come across the second case here, right? We have 2 consecutive red children. And so in that case, we need to rotate right on M, which means that we come across this. Well, now we have 2 red children, which means that we need to flip the color. And by the way, this is a little bit different notation than what I've been using. Basically, this red link corresponds to this node being red. And this red link corresponds to this node being red. So basically, think of it as M and then D and then B. Okay? So the color of the link above the node signifies the color of that node. Okay, so now we need to flip the color because now this is having 2 red children. So we flip the color, and now because D is the root of the tree, everything becomes black. Okay, so now let's try inserting H, okay? So H is between D and M alphabetically, and so we insert it as the left child of M. And again, every time we insert a new node, we want to insert it as red. Okay, well, there isn't any problem here, so we can just go on with the next node, which is S. Okay, X is bigger than M, so we put it as the right child. And now we have, again, the problem of 2 red children, so we need to color flip, making now these black and this red, right? So now M is red. Well, this actually results in the first scenario of having a red right child, right? We always want a left-leaning RB tree to have all the red nodes on the left. So how do we do that? We need to rotate left on D. And once we do that, we actually get this left-leaning RB tree. And the reason it's left-leaning is because now the left node, which is D in this case, is going to be on the left. And the reason D is red is because, apart from the notation, after you rotate, you remember to switch the colors of D and M, right? So M was red here, M is now going to be black here, also because it's the root. D was black here, it's now going to be red here. Okay, so now let's insert E and K. So we're inserting both of them, and they seem fine. They're both red children though, so now we need to color flip, and then now H becomes red, and we know that D is already red. Okay, so again, we have this problem of having a right red child, so we need to rotate left on D. And so we get this resulting left-leaning RB tree, which results in another problem of having two consecutive red nodes, right? And so in that case, we need to rotate right and have this. But again, we have another problem of having two red nodes, which means we need to color flip. And so at the end, everything becomes black because the root also has to be black. Okay. All right, so let's look at some questions. We want to convert this red-black tree into a 2-4 tree. Okay, so remember that all the red nodes are part of the same key as their black parent, right? So we know that 12, 27, and 33 are going to be in the same key. Okay, we know that 8 is less than 12, so by that, and also by the fact that it's just kind of by itself there, it's going to be in its own key. We know that 14 and 25 are going to be in the same key as 19, and so 14, 19, and 25 are going to be here. And you can check that this satisfies the invariant of having to be between 12 and 27. Then we have 31 all by itself. And then we have 46 all by itself. And if you're ever unsure of where a node should go in the 2-4 tree, then you can always try to satisfy the invariant of this having to be less than all the keys, this having to be between the first two keys, this having to be between the last two keys, and then this having to be greater than all the keys. All right, so now we want to insert 13, right? So 13 is probably going to go into where? It's going to have to go in here, right? Because it's between 12 and 27. So let's actually copy this tree. And I'm just going to put 13 here. Okay. But we realize that we have a problem, right? Because it's a 2-4 tree, meaning that the number of keys that we can have is ranging from 1 to 3, right? So let me just I should have reviewed this a little bit earlier, but 2-4 trees means that minimum number of keys is 1, and the maximum number of keys is 3. And remember that number of children has to be equal to number of keys plus 1, right? Okay, so because we have exceeded the max number of keys, we basically need to push up some node, right? And so assume that if a node has 4 keys, we choose to push up the right of the 2 middle keys, right? So basically we're pushing up 19 here. And so let's see what that would look like. So we want to push up 19. So now 19 is going to be pushed up to here, right? So let's actually yeah, we would have to actually push it up here, 19, 27, 33, which would be a really big problem because, hey, we cannot have 4 keys again, right? So, but let's just kind of imagine that we can for a temporary second. So 13 and also 14 is going to go here. And then 25 is going to go here, right? This kind of still this does still satisfy the invariant, but it's invalid as a 2-4 tree because we have exceeded the max number of keys. So what do we need to do? Basically, we need to keep pushing up until we don't exceed. the max number of keys. And so again, we're going to be pushing up 27. So 27 is going to go here. And so 12 and 19 is going to go to the left, and 33 is going to go to the right. And recall that the number of children